Okay, so now we'll try to understand the steady heat conductions in plane wall. So this is pretty much similar concept. We already know conductions and we know the Fourier's law. Here we'll try to understand the conduction, the steady heat conductions. So steady heat conductions. Here we got a picture. This is the wall. You can see the schematic, the directions. You see, we said this is the conduction heat transfer rate. So heat transferred through this wall. Here we said this is steady and the one dimensional. So it is not steady means it will be same with respect to time. It's not changing with time. And one dimensional steady, I already explained, and the one dimensional means it is changing in the one directions. Here we set the coordinate system. Let's say this is the x coordinate, this is the y, and this is the z coordinates. So we said it is actually changing along the x axis. And here's the evidence. You can see this is the wall. We have all the marks, the temperatures. So this is the y axis, this is the z axis, and this is the x axis. So for better, you know, this is the x axis. So when it is the x axis, here the temperature was 20, then here it is 11, this is 3. So it is basically changing along the x axis. If you go up in this way, you see the temperature is 20 along the y axis. If you go this way, you see this temperature is 3. It's in this side it's 20, this side it's 3, in the middle this is 11. So it's not changing in the vertical axis, the z axis or the y axis. It's only changing along the x axis or the perpendicular directions. So we can say the conduction in a plane wall, this is steady and one dimensional. So this is one of the basic concepts. So we'll use it for these assumptions for most of the problem. We'll write it as steady and one dimensional problem. And as the temperature is changing along the x-axis, so we can say it is just the temperature is function of x. So it's because it's only changing along x-axis. According to the the energy principle, what will happen here? The amount of heat is just coming in, this heat in, the heat out. It will be equal to the change of the energy with respect to time. D over dt. This is actually the rate of change, and E is the the energy of the wall. So it's clearly written here, the rate of heat transfer into the wall, heat transfer out of the wall, it will be equal to the rate of change of the energy of the wall. So from this process, we already know from the Fourier's law that this is negative K A delta T over delta x or dt dx. It is the thermal conductivity, this is the area, heat transfer surface area, and this is the temperature gradient, the temperature change delta x. Here we do not need the mathematical calculations. We now if we put it like this, so let's say here the temperature T1, this is T2, we have this small gradient dt, this it was the wall thickness. If we say it is at this position, it is x equal L and x equal 0, this is x equal L. So if we do all these calculations, then from the calculations we will get these expressions. So we do not need this. So you see, here we need to do some integrations. You all are familiar with the integrations. So this limit will be 0 to L, and here this limit it will be T1 to T2. You see, so if we do all this integration, this mathematical calculations, then we'll get this. So this is the the steady heat conductions in a plane wall. Now, important thing, now you need to concentrate. For the steady heat conductions in a plane wall, we all know the